bathroom in here.
So, I'm Catherine, and I'll be talking about the Browning 1917 water-cooled machine gun. So, a little bit of background: they were first used in World War I, right before it ended. They did so well, they saw them again in World War II and in the Green War. These things were really heavy because you had to fill part of the water jacket, all the water jacket with water, so they were more for defensive positions. You didn't really move them around once you set them up. So for air-cooled, the barrel temperatures were getting so high when they first started using machine guns that the barrel would actually have to be changed every hour, and because of that, you would actually see you couldn't use rapid fire. You'd have to shoot in small bursts and then let the barrel cool down and continue to shoot. But with water-cooled, you could maintain lower barrel temperatures. You didn't have to change the barrel because the integrity wasn't destroyed, and you could use rapid fire. So you could just sit there and shoot and shoot and shoot. So how they work: you essentially have this water jacket, like I said. You fill it up with water at the top. Once you start shooting, the barrel will eventually get hot enough and make that steam, or make the water turn to steam. Then it will exit out of that hose and condense back in a pot where you can reuse the water. Or make tea. They said they used to drink, it tasted like straight gunpowder, but they make tea. So your thermodynamic system, you're going to have the barrel of the gun. So there's going to be conduction through that barrel, and then you're going to have convection with the water that's around that barrel, and that will turn the steam into water that exits here. Technically, this is also a thermodynamic system because you're having water condense. Well, steam turn back into water in the condensing pot. So for the analysis, I didn't really know much about the temperatures that were inside the barrel, but I understood the water and how it changed, so I worked backwards to get the temperatures that you were experiencing inside of the barrel. So I knew that the jacket held 5 quarts of water, so I knew that it would take, first of all, it would take this much energy to turn the water from room temperature to 100 degrees Celsius to make it boil. So using that, I found that it took 1,583 kilojoules to make that water heat up to a boiling temperature. And it said that the water boiled after 600 rounds. With 600 rounds per minute, you would have to put in 26.4 kilojoules per second. So after you heat the water to a boiling temperature, you also have latent heat, which is the heat you put in to convert it from a water state to a vapor state. So using that simple calculation, it was 10,666 kilojoules to boil all of that 5 quarts of water. It was shown that it would boil after 21,000 rounds, and using the firing rate, you would put in 5.8 kilojoules per second, shooting, like just sitting there and shooting it to continuously boil off that water in that time frame. So on to heat transfer. Using the 5.8 kilojoules per second, assuming you're standing there and just shooting the gun, you can use your convection equation for heat transfer, and you can find the temperature that's going to be on the outside of that barrel using your given area and your forced convection coefficient. So I found the temperature of the barrel to be 218.12 degrees Fahrenheit, which makes sense because it's going to be above boiling. Well, it's going to be above the temperature that water boils, which is 212. So it's going to heat up that water and it's going to be turning it into steam. And then you also have conduction through the actual barrel. So I assumed it was 184140 alloy steel with a conductivity of 42.6. Using your heat transfer conduction formula specifically for cylindrical geometry, you can find the temperature that is actually on the inside of the barrel. And I found that temperature to be 256.96 degrees at the bottom. So for all these conduction, convection equations of the heat transfer analysis, I assumed that the temperature that you have conducted through the walls of the barrel is the same as the heat, or not the heat, the temperature. The heat that you have conducted through the walls of the barrel is going to be the same as the heat that is convected through the wall. So it's like 100% efficient in that manner. In reality, you would have tons of heat loss through the jacket. It would not be ideal. Also, you have material specifications of the gun. The thermal conductivity I choose for 4140 is not the actual specifications of the gun that was used. ANSI 4140 was actually used in 1920. This gun was used in World War I, which is 1917, and also the steelmaking process in 1917 is not efficient as it is today, so that could definitely affect your thermal conductivity for the material that I used. Also, the barrel dimensions I used in this analysis, which will go back. The barrel dimensions that I used in this analysis, I could not find specs on that, but I knew it shot a 30-06 bullet, so I used the outside diameter of the bullet to get the inner diameter of the barrel. And then looking at rifles around, you could compare the thickness of that. So I inferred the thickness of the barrel looking at a normal 30-06 rifle. And actually added some buffer because back then they made them a little thicker. So, and like I said, the heat transfer analysis I did assumed that all the heat that was conducted went into convection, and all that heat that was through convection went into heating of water. So it was perfectly ideal. So in conclusion, this gun, y'all can read the quote if you want, but lack of time. In conclusion, the gun was great for defensive positions. It really took advantage of like thermodynamics to completely cool up the barrel and make it useful in World War I and World War II. So, are there any questions?
Any questions? Forced pump kind of system, or is it just water sitting in there?
It's just water sitting in there. So you literally pour water in this water jacket, and as you shoot, the water's going to turn to steam and exit through the outlet pipe.
So you have to continually add more water as you're shooting?
Right, but you could shoot for 21,000 rounds. Because all the 5 points of water was gone. So, right here, the weapon fired continuously for 21,000 rounds, which gives you 2,100 seconds of continuous fire before you completely burned off the 5 points of water. That's a lot.
So if the water's just sitting there, is there really that much convection?
Yes, there has to be, because you're turning that water into steam. So you're going to have the heat transfer, you're heating up the actual barrel, and then the outside of the barrel is going to relieve that energy through convection of the water. So that heat that you're convecting out is going to go into changing the water to steam.
The convection is generally to flow across the surface though, so if it's not moving, then it would just be conduction from the barrel into the water.
Okay. I didn't know that. Yeah, go ahead.
I think you were right with the convection, but would it be free convection instead of forced convection?
That's the one part of it.
Okay. So you wouldn't have the convection heat transfer, but you would use, instead of the forced convection H, you would just do conduction?
No, you haven't learned convection, I guess. So if you go to the next slide, there's a couple of mistakes fundamentally, right?
Okay.
The Q is equal to HA times T bar minus T infinity.
Right.
That's what it shows up in chapter 1, correct? Of the
Yeah,
textbook.
that's what I've seen.
Yeah, but internal flows, we don't write T infinity, first of all. Right? When things are flowing, there's no T infinity. It doesn't have a meaning. We use something called a bulk temperature, right?
Okay.
Bulk mean temperature, Tm, right? Which could be changing. We don't know how the bulk mean temperature is changing. The heat being put in, that's changing with time, right? That's Tm. First of all, it's not T infinity, it's Tm.
Okay.
That needs to change. Assuming it's forced convection, which I can't judge, it's probably more likely to be natural convection, right? Which means you check for the Grashof number and the Rayleigh number, right? Not the Reynolds numbers. So
Okay.
you check for the buoyancy of things, right? And then there are different H numbers that show up based on those two numbers, Rayleigh number and Grashof number, Rayleigh number, Prandtl number. Grashof number, Prandtl number together becomes Rayleigh number. Rayleigh number will tell you what the H value is.
So your forced
And
convection?
you never get such high values.
Yeah, it would be way lower.
And that is a value that needs to go in here, which means your temperature becomes really high. So your fundamental effect would be of all this analysis, your H drops, T becomes higher. So your
Right.
T at the end of it would be much, much more than 2.
Yeah, it would be reasonable to see higher temperature.
Much, much hotter.
Yeah.
Because you're sitting at 236 Fahrenheit, whatever, Water won't boil in 30 minutes, whatever it was. Not enough energy is being put in. It has to get up to much, much higher temperatures. But that's okay, it's a good start. And convection is very, very dangerous. We teach it to you as steam theory, but steam theory is something that does not quite show up all the time in convection, especially in thermal flows.
So what do you do is,
We define some of the temperature, bulk neat temperature, and then we do integration for that. And that's what makes your life all miserable. That's what